Hi there, this tutorial will show you how to do an FEA analysis simulation focusing on stress and displacement, and it's going to be looking at a crane. So this is actually a tutorial in Simscale. I didn't draw this myself, but I have created my own copy of it, so if you want a link or indeed want to search for this, then you're very welcome to do that. But it's a section of a crane, and what we're going to do is apply a few boundary conditions to it and look at some forces and define the value of gravity and then run a simulation. So it's a really, really useful thing in engineering. And if you're doing an engineering qualification, which I am with my students, which is the AAQ Extended Certificate of Engineering, then this is a skill which you will need. So my students will be using this. So normally you would need to log into Onshape if you're wanting to export something that you've done yourself, but this is one which has been created already. So you will need to create an account in Simscale, which is free, brilliantly. I just used my Google account details, but you can use your password and email normal way. So to find this, you could go to public projects and type in FE analysis of crane without the JMH copy. But like I said, I'll put the link in the description below. So what you may notice is that the controls are slightly different certainly to Onshape. So it's a little bit difficult to use. I think the zoom is back to front and the right and left mouse button are slightly different, but you should be able to work that out. So we've got a crane. What we're going to do is create simulation. So this should pop up automatically. Create simulation. We're going to have a static simulation, and I think that will be fine. Static simulation. So there's loads of other things you can do. CFD is flow, structural will be FEA. So we're going to create a simulation here. And there's loads of things we could include here, but we're going to keep this fairly simple. So the first thing we need to define is the model, which is basically gravity. So the magnitude of gravity is 9.81 because we're doing this on planet Earth, and the direction is in the Y direction. So if you look at the bottom right, we can see Y is vertical as expected, X and Z are as defined. So we want this in the Y direction, but it's -1, so that's going to be acting down. And this little blue arrow shows us the direction of gravity, which is great. What else do we need? We need to define the material. So if you click on the materials link here in the menu, then there's lots you can use here. So a whole range of different materials. You could search for steel here or scroll down, but just click on steel, and that will define your standard steel. Now there's various types of steel, so this is one particular type, but that's absolutely fine for what we're using today. And then apply, that's absolutely fine. So then we need to, it goes blue when you've given it a material, so that's nice. And then there's boundary conditions. Okay, what are boundary conditions? So it might be obvious that this is a crane to you, but it's not that obvious to a computer. So we need to say, well, where are we going to attach this and where are we going to apply the weight? So this is the end section of a crane, so it's going to be attached at these 3 points over here. I can rotate this round. Oh, I think it might have gone, I thought they'd gone upside down there. So these 3 faces here, we need to specify, and then we're going to apply the load to this box here, the bottom of the box. So these are our 2 boundary conditions. So click on boundary conditions here, and we want fixed support. So on fixed support. We need to click these 3 faces. Now do be careful when you click them that you're clicking the face and not the cylinder. If you do that, then that will get a very different result. So it's given them a name, we don't need to worry about that. Just make sure that it's those 3 ends of the cylinders before you accept. So that's where it's going to attach. We can zoom out a little bit, this is all back to front. And then we're going to apply the force to the bottom of this point here. So this is the end of the crane. So we need another boundary condition, and this is going to be force. Here we go then, that's fine. Force, it's going to be, we need to click on the point of application, which should be this face here. And at the moment, that's the arrow there, I think is a little bit unhelpful because we want it to be a downwards, and we want to do this -1 e to the 5. So that means it's a force acting down, which is a weight, as you'd expect. 1e to the 5, that's 1 times 10 to the 5, or 100,000, and the units are newtons, so we can accept that. Great. So that arrow there is a bit confusing. That's still pointing to the right. I think that just means force. But if you click on, if you highlight or hover over that, then it shows us the arrow acting down. So good, we've got our fixed, our boundary conditions. We've defined the material, we've defined the model. So the next thing is we need to think about the mesh. So the mesh means, well, this is basically how simulation software analyzes all the complex forces and stresses acting within a particular structure. So it breaks it down to lots of tiny little shapes, and we don't need to worry too much about that. If we click on mesh, now I think sometimes, yeah, this has already been done, but we were just going to do a standard one anyway. So all of these, the sizing, the fineness, the curvature, I think these should be automatic, the runtime. What you may need to do on yours is click on generate mesh here, because this one's already been generated. The inspect mesh, we don't need to do that, but we can zoom in and have a look. So all these tiny little segments, this is how it's created, lots of different parts in order to do the analysis. So this is actually very, very complicated. So even though we think it should just be able to do it automatically and very quickly, it's doing thousands and thousands of calculations on all these different parts, and then lots of complicated analysis to give us our final value. So we don't need to generate the mesh, we can just accept that, that's fine. Okay, so we are now ready to run a simulation. So go down to the bottom here, simulation run. Run name, we'll call it run 1. It will say duration 0 to 10 minutes. It'll probably just take less than that, maybe 1 or 2 minutes. We can click on start, and then we may need to wait for a short while. So at the bottom left here, well, here we go. It says the little box is saying it's working on it. It normally, for something like this, shouldn't take more than a couple of minutes, but it will tell us when it's finished, and then we can analyze it. Okay, so that took about 3 or 4 minutes, and then we get this box here saying it's finished. I think you can either click on post-process results or solution fields. I think either of those should work, and then we can analyze the results. Here we go. So there we go, straight into something that looks rather pleasing. Okay, let's see if we can make sense of this. So the parts color, if you click on the filters, so I think it defaults to von Mises stress, von Mises. So this, we know stress is force over area. Von Mises is a generic way of thinking about all the different stresses. So there's lots of stuff going on in this analysis. The von Mises is a way of thinking about a simple generic stress. So we don't need to worry too much about who von Mises was, but this is stress as far as we're concerned. Now, if we rotate this, remember we've got a load on the right-hand side over here. So we would expect to see a large stress at this point of application. So this is one potential failure point. So we can see this is red. So this is 3.27 times 10 to the 7. So it's a very large stress at that point there. And if we rotate this around the other way, if I can rotate this, and again, we would expect to get a high stress at the top point here, because this is under tension, more so than the bottom 2 cylinders. So that's really useful, and we can see how that varies all the way along. So we can use this to analyze potential weak points or fracture points in our design, and also consider improvements. We could also change the parts color to displacement, I think. Here we go. Displacement, there we go. I think it's in the Y direction, displacement Y. Okay, I think that's right. So we can also look at the displacement. So if you click on here to displacement, you could look at X, Y, and Z, but magnitude is probably the simplest. And this might appear fairly small. We can change the scaling factor if we want to. I don't think we need to here. No, I think that's fine. If it was, because it's very, very small, because we would expect, even with a large load, that this crane would only displace a small amount. But we can change the scaling factor if we want to, but I don't think we need to. So let's see if we can understand what's going on here. So remember, the fixed end is the left-hand side, these 3 faces here, and we've got our application of force on the right-hand side. So once again, we would expect this end here to have the largest displacement. And yeah, that's the red. So that's 3.8 10 to the minus 3 meters, or approximately 4 millimeters displacement that we would get on this side over here. So again, as expected, this is where we're going to get the largest amount of displacement or deflection. So as I said at the start, if you want the guidance document that goes with this tutorial video, there should be a link in the description, and I will try to put, or I will put a link to this crane in its original form so you can practice with it. But as I said, I didn't create this. This is actually from a Simscale tutorial. So you may want maybe prefer just to sign up to the tutorial and work through it yourself. But you may find this useful, and I hope you do.